About today's distinguished lecture, we have today Professor Sanjeevi Kumar Padmanaban as a distinguished lecturer who received a PhD from University of Bologna, Italy in 2012. He is currently full professor in electrical power engineering at the Department of Electrical Engineering, IT and Cybernetics, University of Southeastern Norway. He has authored over 600 plus scientific papers and received the Best Paper Award from IEEE, IEEE, IET, IEEE GPCOM 20, and also received 5 Best Paper from Springer Lecture Notes in Electrical Engineering. He is a fellow IE, he is a fellow of IETE and fellow of IET UK. He received a Lifetime Achievement Award from Marcus Who Is Who USA in 2017 for his contribution to the power electronics and renewable energy research. He is listed in the world top 2% of scientists from 2019 by Stanford University, USA, EU Tech researcher in long duration storage technologies among 52 researchers and professors from EU from 2023. He served as an editor of IEEE System Journal, IEEE Transaction on Industry Applications, IEEE Access, IEEE Transaction on Power Electronics, IT Power Electronics, IT Electronics Letters, and the subject editor for the IET Renewable Power Generation, also IET Generation, Transmission and Distribution, and Facet Journal from Canada. He have IEEE System Council position history. He worked as a distinguished lecturer from 2023 to 2025. About today's distinguished lecture, the title is Renewable and Modern Control Power Electronics Technology, and which focused on the renewables, particularly PV, solar, battery, fuel cell, wind power are going to have a predominant business for the next 50 years. State of the art technology, newly developed control strategy as an example with hybrid ANFIS PSO and Lapnow function for power converters, configuration for fuel cell, and also he will discuss about new power converters with new modified versions are viable and cost effective solution as a power electronics technology. So I welcome Professor Sanjeevi Kumar Padmanaban for this lecture and welcomes to you, Professor.
Thanks a lot, Professor Zahar Mahajan Bhaskar. Thank you for giving me a brief introduction. Could you please allow me to share my slide? Today I like to present on the topic of renewable and modern control on power electronics technologies, what we have been developed from past 10 years plus, along with my researchers across the globe, as well as currently working various researchers. I'm from University of Southeastern Norway, from the Faculty of Technology, Natural Science and Maritime, which is the location of Nordic region in the Norway. We have 8 campuses. I'm from Prosgrunn, the top view of the university, a beautiful location in the southeastern part of Norway, a city called Prosgrunn. And this is my university where I am talking currently for this distinguished lecture. So today about the distinguished lecture, I like to emphasize what I'm going to present is on hybrid renewable energy systems. And today hybrid renewable energy systems are the major aspects of renewable technologies for next 50 years, which includes photovoltaics, wind, batteries as a hybrid renewable energy systems to have a clean, green and noiseless environmental free power generation, which is the goal of all the nation for 2050. And of course, I'm particularly focused on providing some solution where we also focused on agricultural harvesting by using power electronics solutions for water pumping, irrigation facilities using low cost solutions. For these is very important with photovoltaics, which is maximum power point tracking, and we develop many algorithms which can able to provide you an optimal solution and fast tracking for different environmental conditions. For example, we also develop a very advanced artificial bee algorithms, which is called ABC, along with a new modified MPPT algorithm, which is a maximum power point tracking, which can provide simple implementations and more accurate and ability to adapt at the different working conditions. I'm going to present today about this distinguished lecture. So the most important is the hybrid renewable energy systems. What is an hybrid renewable energy? When we are using multiple renewables, for example, wind, photovoltaics, and they are of different power levels. Photovoltaics maybe 10 gigawatts, wind can go up to 12 megawatt capacity. So there is a big power balance difference between two different renewables. And these are how we integrate with the grid. That is a big challenge for the power electronics engineers. And in this case, a simple photovoltaic module can be moduled by using a current source device connected with diode and series and parallel connected resistors to show a simple model of a photovoltaic module, which is a basics. We are integrating the wind turbine using a permanent magnet synchronous generator because it can easily control the wind velocity by using the torque angle delta, and we can able to control also the power factor very effectively. So the modern wind turbines are using more permanent magnet synchronous generator, which we connect to a rectifier, a standard uncontrolled rectifier. Then we fed to a power electronics device, which is a converter, because to balance the voltage generator from synchronous generator to step up to the requirement of the inverter, which converts the DC to the AC, and we are connecting to the induction drive systems and other application of a centrifugal pump, which can be used for irrigation facilities. Parallelly, we are also using photovoltaic panels. The photovoltaic panels are connected again back to a converter, which can work as a boost or step up voltage regulator, which is connected on the diesel link in parallel to the power generation from the wind turbine. Plus, we also connecting the battery, because batteries are the backup generation. When there is an excessive power from the wind, we can pump the power to the battery, we can store. Or if there is an excessive power from the photovoltaic panel, we will store in the battery. And there is a peak saving conditions where photovoltaic or the windmill doesn't able to provide the sufficient power. We pump the power from battery to the inverter to keep the irrigation systems continuous propulsions. So in this case, what we have done, we developed new algorithms on MPPT, maximum power point tracking, by using ABC algorithms, where we try to figure out the voltages from the panels and the current. Also, we adapted a space vector modulation, because space vector modulation can able to provide you more fundamental components and reduced harmonic distortion with your AC voltage, which is connecting to the centrifugal pump systems. And for this purposes, we are using particle swarm optimization algorithm, which develops the triggering angle for the space vector modulation. So we have developed a new control algorithm, which is based on ABC. And of course, we try to control the space vector modulation by using PSOs. So these are the novelties we try to develop for irrigation facilities. In this case, we have also shown the relationship between the tip speed ratio and the coefficient performance of the turbine, and various angle at which we can able to see when beta is equal to 0, we are near to 0.5, which is the coefficient performances. As the beta varies to 5 degree, 10 degree, 15 degree, and 20 degree, we have a variable speed driven from the wind turbine. But by using the MPPT algorithm and space vector modulation, we try to provide a high quality waveform to the centrifugal pumps. In this case, we have developed some algorithms on the based on the real scenario interfacing with the DSpace and MATLABs. So in this case, we used around hydration for 50. The runtime is 15, and the desired cost function is a 10 power minus 6. And we also use the foot source for calculation of ABC by using 20. And B algorithm used with employed 10, and number of onlooker B's is around 10. What is the algorithm we started? We started the function. We look for the feed algorithm parameters, which is taken from here, and specific power system parameters we calculated from the grid, and we start the foot source duty and rotor speed randomization. So this is the first step we started. Then we try to find what is the fitness function which is required for all these parameters to be optimized. Then we try to update the employed B by using check converters based on the rotor speed. Then we try to optimize or probabilize the calculation with the greedy selection process to calculate the appropriate value of the duty ratio, the speed of the rotor, which the B can greedy selection mechanism. Then we evaluated the duty ratio changes and evaluate them. So if the process are done in hydration equal to hydration plus 1 time, then we try to find the hydration is equal to maximum hydration. If yes, then we try to go for a duty ratio equal to an optimal duty ratio is fine to control the cuck converters. Suppose if the hydration is not maximum, then we try back to the fitness function. We update the fitness function until we obtain the maximum hydration number to get an optimal duty ratio for the power electronic DC converters. And about the control scheme, how we have developed. So we try to keep the reference as the speed of the rotor, and we adapted the standard V by F controls is the most easiest way of adapting scalar control of the induction drive. So we set the speed reference of the rotor compared to the actual speed. Then we try to regulate the PI regulator in online based on the error function. We using particle swarm optimization. We try to tune online the parameters of Kp and Ki until an optimal value is obtained in the controller. Then the reference, the output of the PI regulator is compared, which is a synchronous speed, is compared with the actual rotor speed to calculate the difference between the speed and given to a gain parameter. And this gain parameter is again given to a V by F controller. The VF controller will have a lookup table which regulates between the voltage and frequency. Then again, we transfer the frequency and voltage into ABC parameter to get three variables, which is the duty cycle for the three legs of the inverter. Then we convert them into alpha beta because we are using space vector modulation, which is a more optimal modulation to get high performances of the drive with reduced harmonics. And these signals are fed to the inverters. So we are able to drive the centrifugal pump very effectively with a standard scalar vector control, scalar V by F control, and we have not adapted any very dynamically controlled or a very complex vector control. We never use. We use a simpler V by F control is the most easy way, but we optimize all these parameter by adapting AI algorithms to make it more similar to dynamic vector control. And this is the state of vector where we are controlling the PWM of the space vector modulation in each 60 degree of its rotation in 360 revolution of the cycle. And we are able to provide an optimized switching pattern in the inverter to generate a lower or reduced harmonics and a high rate of reduced THDs, total harmonic distortions. About the PSO, how we are tuning the PI regulator, the values of proportional and integral constants. So here the purpose of the PI based particle swarm optimization controller is to reduce the error. For this purpose, what we are doing, we are trying to get the slip speed and we are adding to the rotor speed so that we produce a new stator speed which can be able to control the induction motor very efficiently than a standard V by F control. And of course, here the major challenge is when we are comparing with ABC based algorithm is very slow with the velocity of convergency when compared to PSO algorithms. But that there is a trade-off for the PSO based PI regulators is more accurate, precise, stable, and it can be under highly dimensionally optimized problems. And of course, in this case, ABC algorithms, when we compare, we are using MATLAB coding to compile with the D space, which requires a high convergency period to tune the parameters of the PA regulators of the induction motors. So what we are doing in our proposed method, we start the algorithms. Initially, we initialize the velocity and the position of the swarm particles. So these are calculated based on the induction drive parameters. Then we try to evaluate what is the fitness function. Once the fitness function is fine, we are trying to determine what is the Kp and Ki new value specification. Then we are running the motor for the control to decide reference value. Then we are investigating what is the performance characteristics obtained. If it is found and the conditions are satisfied, we are stop regulating the PI regulators with the required values. If the conditions unfound or not satisfied, again we are feeding the parameter back through updated values to the evaluation of new fitness function. Then until it finds the right value of KP and Ki, the algorithm will be automatically in loop to find the new values. About these setups, we are tested in the laboratory condition. We created a emulsion model of the permanent magnet synchronous turbine linked wind turbine. So we created a module and we have a check converters inverter which is connected to the centrifugal pumping systems, a D-space and photovoltaic model at low scale in real time, which is pumping the water in the tank is an example we have took. For this purposes, we used around the PV power rated to 220 watts, wind turbine which is around 160 watts, and normal operating frequency which is chosen 50 hertz, and the stator resistance is 4.62 ohms, rotor resistance is 3.93 ohms, and number of pole pair is 2. The rated speed of the induction drives pumping system is 1800 rpm. Then we try to regulate all these performances with two different controllers. One is we use ABC based maximum power point tracking algorithm. Another one is the PSO SPM PWM based inverter control. So we had a comparison for these hybrid power system control algorithms. We find with the PV and wind both. In case of ABC algorithms, the duty cycle generation is optimal, but when compared to PSO SPPWM, where we get more optimal power extraction from the wind, and PV when compared to ABC based MPPT algorithm. If the wind is alone, we find that with the ABC algorithms, the duty ratio generation maintains DC link voltage. Only we are able to maintain the DC link voltage of the inverter, whereas when we use a PSO based SPPWM, we are able to generate the current signals which makes the optimal power extraction from the wind turbine, which is connected with a permanent magnet synchronous generation. So this is more optimal because we are directly controlling the current parameters, which makes the maximum extraction of the power from the wind turbine. When only the PV is alone connected, the ABC algorithm is not very effective. The DT ratio generated was absolutely zero, so you are unable to generate the power through the algorithms. Whereas when we use particle swarm optimization based space vector modulation, we are again controlling the currents which can be able to extract the maximum power from the photovoltaic panels from each module. So the algorithms what we developed to control the space vector modulation for a induction centrifugal pump drive is more effective when compared to the ABC algorithms we tried in different AI based applications. This is a module which we used in MATLAB linkage with DSpace. You can have a look how we used three different signals integrated to convert into alpha beta parameters in a stationary reference frame. Then we able to trigger the values of the space vector modulator, which can be able to control both speed and torque. And this is an example how we are converting the alpha beta components into a S function parameter, which is required to drive the inverter's output through the DSpace various output bit signals. And this is a filtering unit because of all the signals we sense from the real induction drives and grid are having a lot of distortion. So in order to avoid that, we use filters and we use MPPT to control the maximum power point tracking from the photovoltaics. Then we connect it to the DSpace for controlling the inverter PWMs. Similarly, we also use a DAC, digital to analog converter, to look at all the parameters which is going inside the converters and the calculations what we are getting are optimal. So this is a complete module which we try to make more optimized integration between MATLAB and DSpace. And these are some of the experimental results what we got. This is with respect to the time varies from 0 to 1000 time scale, where you are looking at the wind speed in minutes per second. You can have a look how we varied the wind speed from a value of 22 to 21 regulations to show some variation in the wind speed at different frequency. Then this is the variation of the wind power. You can have able to see there is a lot of fluctuation in the wind power, around 150 to 100 watts low power application we tried in the laboratory scale. There are a lot of oscillations available with the wind turbine power generation. And this is the duty cycle which is generated from the Cuck converter, which integrates the wind turbine to the inverter. So the duty ratio varies slightly higher from 0.82 to zero point 0.7 at the end. There is a lot of fluctuation. These all created because of the huge fluctuation within the wind turbine power generated. But by using space vector modulation and AI algorithms, PSO algorithms we are able to provide the battery current. You can have a look. We are trying to regulate the battery current at different intervals in the system, say around 0.44, 1.6, and 4 and 4.8. We try to regulate the different power. The battery currents are more smooth and periodic. There is no any huge harmonics which is generated from the frequency variation of the wind turbine is not visible in the batteries. Of course, this is the current which is connected to the grid current are very smooth. We are shown in the DC components in order to show the regulations are very dynamic. And this is the current regulation from the photovoltaic panel in the beginning, which is around 8.2. Then it is step down back to around 6 amperes. We are regulating to show the variation of dynamic performances are very smooth with the proposed control algorithm what we develop with AI technology. And this is the current through the induction pumping system, which is used for water pumping and irrigation facilities. For the end users, the current reaches around 18 ampere during the first propulsion. Then we try to regulate the variation of the speed, regulation of the power, regulated variation from the wind turbine and photovoltaics. All these variations never affects the behavior of the centrifugal pumps, except some few transient occurs. This is obviously happen in any system. And this is the dynamic behavior. We are very inside to look at what is going on during the startup transient, steady state, and dynamic operations. So this is the power which is the voltage generated from the photovoltaic panels. You can have a look. There is a lot of oscillations, sustainable oscillations happen in the steady state period with the photovoltaic panels. And these are the currents which are having huge fluctuation between zero and the peak max from the panels. Then this is the total power, when the total power is also having a lot of oscillations created from the real parameters. Then we try to control all these parameters through the controllers and cut converters with our PSO and optimized space vector modulation operation. You can able to see the current generated from the power, which is able to have a very smooth regulations. There is no any huge perturbations or subharmonics generated either in the voltages or current or total power. So we are trying to keep always the maximum power with the maximum limit or the margin, even though there is a huge power regulation variation from wind turbine and photovoltaics. Always we try to keep the photovoltaic power maximum at the MPPT by controlling the duty cycle of the Cuck converter through PSO optimized modulation index. And this is the overall power voltage which is regulated from the panel. Even though there is a lot of huge variation, its stable output is obtained. And this is the current which has been regulated from minimum value to the maximum, and the power also regulated from minimum to the maximum. All these regulations, very smooth propagation has been created, and which can be able to be seen through also the maximum power point tracking, where we shown between the voltage and the power. And these are the parameters we are looking at the inverter point of system, where the DC voltages of the inverter is almost 1200 volts. We try to maintain, and this is the torque generated by the induction drive system for the pumping. And these regulations are created due to the fluctuation of the wind turbine with different powers, photovoltaics. That's why we got these oscillations a transient period. Apart from that, it's producing a smooth torque. Of course, the speed is very smooth, and the current through the induction motor drive are more sinusoidal, and very smooth operation is obtained with our experimental verifications. And in order to look at very smooth behavior of the system, the most important is we try to keep always the unity power factor. So the green one is the voltages generated from the inverter, and we have the red color, which is the current. They are almost sinusoidal throughout the system operation during different perturbation from the wind and photovoltaics. This can be easily visualized here. We try to have the flow rate of the system from zero, then at around point 9, we are trying to increase the flow rate from zero to the maximum 110 flow rate I per S. So this is the maximum value we reach. Similarly, the head is reaching from zero to the maximum when we start increasing the flow rate. So all these conditions, if you look at the drive systems, it provides a high quality waveform with unity power factor control. And the most important is the ambient condition where the sun is having insulations. We try to create the insulation artificially by using the PWM methods. So in the beginning, we tried to keep around 1,000 watts per meter square. Then we tried to go down for 50% less, around 500. Then we moved to 800, from 800 to 300, 300 to 600. If you look at all these insulation condition of sun, still we get the unity power factor driven to the induction motor drive for centrifugal pumping. And the most important, the DC link voltage doesn't produce any huge fluctuation between zero and the maximum, which is very dangerous for the photovoltaic systems and wind turbine. Here we are trying to keep very smooth DC voltages, which is rated around per scale of 80 volt. And this is the smooth operation of the current, which is very important to control the required performance of the induction drive systems, which is very smooth and very periodic sinusoidal operation has been observed under huge perturbation condition of sun insulation conditions. And still we want to look very closely how the behaviors are going with these power electronics converters with different AI based, artificial intelligence based particle swarm optimization, fuzzy logic or ABC control algorithms. We are looking the dynamics behavior of the systems. So this is a duty cycle which is created because of the PSO algorithm. You can see that a lot of transient happen, and the duty ratio is varying between the minimum value of 0.55 to the maximum goes to 7.2 at different perturbation conditions. And this is for the fuzzy logic system. Still it goes more higher, which is going to 8. The duty ratio requirement is very high for the DC converters, which is regulating the inverter. But if you look at the ABC systems, it's also the similar way, but more smooth performances can be observed when comparing to other two algorithms, which we closely observe the parameter through digital to analog converters. And about the tracking power capability is very important. How we track with the different algorithms, what we tried in the laboratory test systems, particle swarm optimization, and organic algorithms or fuzzy logic or ABC algorithms. We have shown the performances here. So in the case of PSO, it's huge fluctuation between 50 to 200. You can have a look. The spectrum of oscillation is very high. When we are looking at the power is also having more oscillations when compared to PSO for organic algorithms goes on near more than 200. So you can have a complete view how the spectrum distribution has been having different powers, watt per time like scale. And this is for a fuzzy logic based control algorithm. When comparing to other two, we are getting much better power fluctuations and control when comparing PSO and colony algorithms, optimized algorithms. Whereas in case of ABC is the best one because we got very smooth regulations with various power variation of the photovoltaic panel between 1,000, 500, 800 and 300 and 600. So this is a very classical behavior. The optimized parameter we observed with this dynamic behavior of the PV panel inside the system. We measured all these parameters using digital to analog converter, which is available in the DSpace system. And in order to look at a very close behavior, we are trying to also look at the convergency responses of a different algorithm. For this purposes, we try to find the number of iterations and plotted against the run graph by for the different algorithms, ABC, PSO, and colony algorithm, optimized algorithms. If you look at it, the PSOs goes the minimum ranges around 12 to 11, whereas if you look at it goes the maximum value around 50. Whereas for the ABC algorithms, it's always less than 10. The peak maximum goes near to the 10, whereas it's always optimized near to the 5 in the scale. You can have a look. And the minimum value is around 1 or 2, which is more optimized when compared to Algoni optimized algorithms or particle storm optimization algorithms. So ABC provides more optimal results, more less number of hydration is required and more accurate. Still, we are looking at the accuracy with respect to the runtime. These are the comparison between the PSO and ABC algorithms. So ABC algorithm provides around the accuracy, which is 10 power minus 9 to 10 power minus 11 scale, which is more accurate when compared to the PSO, which is giving an accuracy between 10 power minus 6 to 10 power minus 7, which is a little more higher. You can have a look. So the accuracy provided by ABC is more aspired fitness function when compared to the PSO. So then we try to show logically between the runtime and convergence speed. You can have a look the level which the ABC algorithm produce much higher than fuzzy logic. The fuzzy logic is producing much higher than or colony algorithm optimized algorithm, whereas the PSO is producing the optimal algorithms in the one quadrant operations. And about the tracking future, that's very important. During a partial shading condition, we try to analyze the photovoltaic systems, creating a lot of partial shading condition in the panels. So in the case, we have used 3 different patterns, and the 3 different patterns, the PSO is providing between 99.3 to 99.3 accuracy, whereas ant colony algorithm is providing 99.4 to 99.3, and the proposed ABC algorithm is much effective because it's 99.9 to 99.96, which is more accurate when compared to other algorithms. And these are the various parameters we are inside look into the panels for the voltages. This is the PV voltages. You can have a look, which is regulated from the maximum value. Then we created some partial shading algorithms, so the voltage comes down again back to the required values. It's regulated according to the requirements. Similarly, the current follows the regulation during the partial shading conditions. And these are the patterns we created for the overall power, which is regulated based on the 3 different patterns from the partial shading conditions. And this is for an ant colony algorithm. This is for particle storm optimization algorithm. So here also you can have a look. It is looks very finite value we have to be calculated because we are looking at what are the oscillations created within the systems during the 3 different partial shading conditions we created at different power levels, and it is observed shown here for ant colony algorithm. If you look at the ABC algorithm, is more smooth. We are reducing all the transients very high effectively, and the power generated with the voltage and currents and the overall power is very smooth when compared to other 2 algorithms. That's why we developed the new ABC algorithm is producing the more effective power generation from the hybrid renewable energy systems. We also worked on a combination of photovoltaics and fuel cells, where we use photovoltaic panels and fuel cells, because fuel cell is going to be the future in the electric vehicles, where the primary powertrain will be the fuel cell. So we try to create a microgrid systems where connected to the grid as well as highland modes, so that it can be very effectively used for the future AC or DC microgrid system for charging electric vehicles. So in this case, we use photovoltaic panels, and we also used fuel cell systems, which is integrated to the DC bus of a standard inverter we used here. A 3-phase inverter. Then we design a new LCL filter to control the square waves into a sinusoidal voltage with reduced harmonic distortion to the grid system. So we didn't use any huge transformers to connect between the inverter and the grid. we use directly the LCL filter, which is more optimized to have in very low values on inductors on the grid side, as well as the inductor on the inverter side with a capacitor. So we try to keep a very stable current and voltage connected to the grid. And this is an equivalent module of your simple fuel cell. How to have a equivalent electrical circuit. This is a farmer and a stack unit, which is represented in the form of simple resistors and capacitors. And this is an equivalent circuit of polymer electrolyte membrane fuel cell or proton exchange fuel cell equivalent circuit, which is having a voltage source which is connected to a series combination of two resistors in parallel with the capacitors, and we have a terminal resistors and load resistance, which is a simplest way of representing a large fuel cell system. And here we are trying to adapt a new control algorithm which has not been tried by different researchers. We used a Lyapunov control algorithm. Here I don't want to talk more on the background of the equation. So in this case, we tried to use a PLL, and we are also using a three-phase current which is converted into a DQ axis, where we have two components of the current, and the component of the active power is compared with the reactive power compensation to feed back to calculate what is a Q component. Then we are also using three voltages, which is from the grid system, is converted into DQ. Then we are calculating what is the IQ value and beta Q, which is the Lyapunov function. This is the Lyapunov function we try to adapt to calculate more optimized parameter for your active and reactive power, which is again back to converted from two component to three component values. Then we fire the inverters through modulation methods. What is the advantage of going for a Lyapunov control algorithms? In the later analysis, we use Lyapunov control algorithm to avoid PLL, because PLL is again a PI regulator, because inside a PLL we will have an integrator and proportional constant which is used to track the frequency of the grid system. But at lower frequency, the PLL are not very effective. So we try to remove this PLL by using a Lyapunov control algorithm, which can directly estimate the value of the frequency of the grid systems without having a PLL, which is very ineffective with a low frequency operation, particularly with respect to a wind turbine. So we are using these control algorithms to optimize the value of estimation from the wind turbine and the grid to have more accurate frequency synchronization with the inverter. And this is the VI characteristics of the fuel cell, what we seen in the real time integrating these algorithms. So V is the fuel voltage and fuel current. As at the fuel current is zero, the maximum voltage is in the active region. Then it moves to the ohmic region, and the third one is the concentration region. These are the three regions of the operation of your fuel cells, which is absolutely controlled by the Lyapunov control algorithms to optimize the parameters. And this is the characteristic of power and current with respect to the fuel cells. So as the current increases, the power increases to the maximum. We try to get around 182 volt voltage maximum. Still, if we increase the current, then it starts tripping out. So this is the real characteristic of a fuel cell, what we tested in the lab, and we find all these through with a real implementation of a very complex control algorithm, which is very sensitive to small frequency variations or speed variations of the drive systems. And in this case, these are the typical experimental results what we obtained from the real time. For this purpose, we used a PV rated voltage of 25 volt and the current of 8 amperes. The grid is around 230 volt. Grid current is 30 ampere, and fuel cell we used 25 volt 8 ampere, which is having an electrolyte of alkaline. And anode and cathode coefficient transformation function is 0.3 and 0.5, and electrolyzer temperature which is around 50 degrees centigrade. So in this case, first we are looking at how the tracking has been happened from the photovoltaic panel when there is a solar insolation level and partial shading is happening within the systems. So here, if you look at the power generated, so in the beginning we kept the photovoltaic power zero, then we start regulations. There is a huge transient, then we reach the rated power of the photovoltaic panels here. Similarly, the voltages are shown during the transient condition. There is a huge fluctuation. Then it reaches the steady state condition, and the voltage per division is 25 volt. And this is the current. We having the same performances during the transient condition, and steady state we reach the required current. The scale deviation is 8 ampere per division. And this is all we have done. The insulation conditions, you can see the insulation condition of the panels. Then we got the required power rating. Similarly, partial shading condition has been tested. So in the beginning, we kept all the power requirement of the panels zero. Then we started the partial shading conditions. The huge fluctuations has been happened during the transient period. Then we reached the required power of the panel. Even under the partial shading condition, the required power we generated from the panel by using these power electronics inverter systems by controlling the modulation index. And these are the results what we are looking at the point of fuel cell. So the fuel cell current obviously generating huge oscillations. You can have a look at the required rated current of 16 amperes and fuel cell voltage which is around 11 volt, 11.2 volts. Again, there is a sustained oscillation is generated from the fuel cells, and this is the overall power which is around 150 watts from the fuel cell, and there's a huge oscillations created. And all these oscillations from photovoltaic and fuel cell, still we are able to generate a high quality current by adapting the proposed control algorithms. When the proposed control algorithms we are trying to use, you can able to see the apparent power smooth regulation from 11,100 to 400 and 400 back to 700. We try to regulate the different power, and by adapting the proposed MPPT algorithm based on LiPno, we have a smooth regulation of PV power. You can compare with your. So we got a very smooth power, smooth regulation during insulation condition and partial shading conditions. And of course, we are looking at the total harmonic distortions even in the photovoltaic kernel, which is around 4.3 percentage. And there are smooth regulation of current when compared to the conventional algorithm. So these are the real happening in the systems when we are using a conventional control algorithms, but by the adaptation of the LiPno control algorithm, the spectrum become very smooth, and the required performance are with respect to the IEEE standards, because we produce a 4.3 percentage distortion, which is absolutely required for the system. And we are looking at again very inside the system during a different insulation conditions. So this is the results we obtain by using LiPno control and partial shading operation. There is a huge oscillations voltages and current. Whereas if you are using a conventional PI regulators or fuzzy logic controllers, you can see a huge oscillation has been created during the partial shading conditions or insulation condition, where the total power, voltage or current are oscillating undesirable values. Whereas by using LiPno control, we control to the best possible distortion having 4.5 percentage. And if you are looking at the performance index between the fuel cell performances with two different controllers, we tried to propose a LiPno control, and we compared with the conventional fuzzy and PI controllers, where if you look at the characteristic from the proposed control algorithm is very periodic, very linear function, and reaches the required voltage of the fuel cell. Whereas if you look at the conventional controllers, they are working in a non-system linear functions, but they still reaches, but the performance index created by the proposed system is very smooth and very periodic. And these are the results what we obtain for the fuel cells and PV with respect to the fuel flow and time. You can have a look how very smooth propagation has been created for the fuel cells, very smooth regulations for the required fuel flow, which is around 70 percentage. Then we create some oscillations, perturbations. Still the perturbation is created. Then we back to the power to zero. Then back again to the power which is greater than 80 percentage. Still the system works to the requirement with respect to the fuel cell. That's very important because fuel cell electrolytes are very sensitive to the variations. And with the power electronic high frequency switchings, they can be easily deteriorated, and the reliability of the system can be a big question. Of course, we are with respect to the photovoltaic panel, all these regulations, you can able to see that in the beginning we kept the photovoltaic panel power requirement is zero with the flow fuel flow. Then we start increasing around greater than 30 seconds. We are regulating the photovoltaic panel linearly with respect to the rated power requirement, which goes to the peak. then again backs to zero. We try to regulate all these conditions parallelly operating the hybrid renewable system between a PV and fuel cell. All this case, the regulations obtained are very smooth and very periodic. So the parameters we can able to estimate for the rise time, which is 70 milliseconds. Peak overshoot is 10 e power minus 2 percentage. Settling time is 105 milliseconds. Steady state error, which is around 2.5 into 10 power minus 1 volt. So how we have done all these variations, that's very important. We try to change the temperature, which is around 222 to maximum 344 Kelvin. Then we back to 312 Kelvin. So this is a regulations we created by controlling the signals within the control systems. And these are the performance we able to see between ideal conditions, PSO based OD algorithm what we proposed, and conventional perturb and absorb MPPT algorithms. All the cases, what we proposed OD PSO method as producing the most effective optimal solution between these two algorithms, because in case of ideal it is behaving much higher than the required values, and conventional PSO is producing the value which is less than the required parameter. So the proposed algorithm is more robust as it's more artificially controlling all the parameters based on the design values. We are getting a very proper flow of fuel cells. That's very important in order to keep the fuel cells very active and to produce the maximum power out of it by avoiding durabilities. I mean, the reliability issues created for the electrolyzers. And about other aspects, what we are also working on microgrids is we are working on a global tracking system to have an hybrid model of neural networks, fuzzy and particle storm optimization combination, a modified MPPT algorithm. This makes the more AI algorithms to be more robust. In this case, we are always adapting this system for a global power point tracking under different weather conditions is our goal. And we always compare with the system with available classical models like perturb and absorb, hill climbing, and incremental conductance. These are the three standard MPPT algorithms which are used in practice, but there is a problem because we have power loss and the calculations are a bit complex with these conventional MPPT algorithms. So as I said, we are trying with a hybrid module of not only the renewable energy system, also the algorithms, which is a combination of an adaptive neurofuzzy interface systems plus particle swarm optimization. We combine together, we are able to provide rapid convergencies and low tracking period. The convergence is very faster and the steady state error is very minimum, and we are able to provide a high tracking efficiency as a modern MPPT algorithm for robust operation. This is an example what we have tried in the real time. So we have a photovoltaic panel. For this purpose, we use a zeta DC to DC converter to pump up the power of the DC voltage to the high level to connect with a standard three-phase inverter. Then the three-phase inverter is connected through a grid system through modern metering systems. We use net metering systems. Then it also parallelly connected to the different loads. Here we proposed a new space vector modulation, which is based on ANFIS and PSO based MPPT algorithms. So these ANFIS and PSO will control MPPT. Also, it will control the modulation requirement for the space vector modulation. So we use the implementation using a DSpace DS110, which is a low sampling rate DSpace, but still we able to provide a high convergency rate by controlling the adjusting the algorithms with the new constraints. And this is the simplest form of a DC to DC converter, which is used as a interface between the photovoltaic and three-phase inverter, which is a zeta converter, which is a non-inverting output voltage, which produces a high voltage when compared to the panels, and we get a high voltage which is integrated to the inverter. For this purposes, we use different inductors, zero point 0.5 millihenry and 0.6 millihenry capacitors, 800 microfarad and 1000 microfarad, and switching frequency we kept 6 kilohertz, which is very optimal for the DC space control, and the ripple current, which is around 2.5 ampere, and ripple voltage is 610 power minus 2 volt for the proposed hybrid ANFIS piezo grid connected microgrid systems. For this purpose, we have three different aspects. So the first one is a neural network. We use a 5-layer neural network with the two inputs and one output layer. So one outputs, we have 5 different layers for the weights and bias, and then we used a tan sigmoid function to calculate the required output function. And this is the standard algorithm we used for fuzzy logic interfaces, which has a 7 rules with 49 rules. There's a 7 variables we used. As we know the basics, so normally big, normally small, normally medium, like that. We use the algorithm, a standard fuzzy logic algorithm, but we fine tune the values for the requirement with small adjustments. Then we implemented this in a D-space system where we tried to modeling a PV system by using MATLAB and Simulink. We collected all the data from the PV system. Then we used a collection of fuzzy data. So the fuzzy data is available here. We inserted this function. Then the application of fuzzy interface rules are used. 49 rules we have. The 49 rules are used here. Then we implemented the combination of neural network combined together here. So the next stage is the neural network. Then the neural network output F, we try to check here if the error is less than the maximum error, then we try to go for the trained model using PSO. If the error is greater, then again we update with go for the fuzzy logic membership function to cross check. If the error is minimum, then we train the model of the PSO. Again, we check the error. If the error is less, we connect to the PSO and phase control algorithm for tracking the MPPT and controlling the space vector modulation. If the error is greater, then again we feed back to the membership function to update the new value of F by the combination of fuzzy and neural network. So this procedure is automated and continuously monitoring all the parameters indigenously with the DSpace system. And this is an experimental model we used for the testing. We have a particle size of 50, number of iteration is 50, the inertia is 0.8, and number of epoch we use is 100. Data set is around 180, and membership function, as I said, in the 49. This is an experimental setup. We use photovoltaic panels. We use the D-space, inverters and zeta converters, and flux scopes for analyzing all the parameters for standard IEEE standards of total harmonic distortions. And we adapted 2 methods. And hysteresis control based space vector modulation we tried here. So we tried to have the current of the active power and reactive power. Then we converted these currents into stationary reference frame, and we feed to the hysteresis space vector modulation, which controls the inverter. From the inverter point of view, again, we calculated the currents, which is restructured for calculating the value of alpha and beta, which can able to control active and reactive power. We feed back to the system. So this is like a closed system which synchronized with the grid, and we kept the band for the limitation of harmonics. So we use hysteresis controller, which can fix the maximum value of the current and the minimum value of the current, with which the current will oscillate in this limit, both in the positive and the negative cycle. So the harmonics are well controlled by using hysteresis band and space vector modulation to have an optimal results by using ANFIS, PSO, MPPT algorithms. And this is the module how we develop in MATLAB interfaced with the D-space. We use the ADC channels buffer for controlling the oscillations in the currents and voltage and frequency. Then we calibrated it and we connected to the external terminals of the inverter drive systems. And here you can able to look at how we are controlling the photovoltaic panels, the power and the voltage we generate from by using ANFIS tool. We control all these MPPT. Then we are controlling the PWM of the D space. So these two way we able to generate the instantaneous power and pulse width modulation of the inverter. The most important is the grid voltage, which is more sinusoidal out of all these perturbations from photovoltaics and other renewables, which is connected with the system. And this is the grid current we have shown very smooth. And if you look at the grid current and voltage, we are trying to keep unity power factor. So these are the grid power factor variation at unity, more sinusoidal, and the required performance are obtained with a harmonic distortion less than 5%. Then we try to introduce the inverter pursuance in order to understand behavior of the inverter. We tried artificially, we the modulation index, we introduce additional harmonics. We introduce a fifth harmonics seventh harmonics extra. Still, the current is unity power factor, but slightly distorted because we introduce additional harmonics to see how the system behaves with the grid. And these are the performances we got with total harmonic distortions. So the total harmonic distortions is around 6.5 percentage for the output voltage, and sorry, 2.6 percentage for the output voltage, and 2.8 percentage for the output current. And this is the regulation of the photovoltaic panel has been shown here. The power is regulated in different means. We are trying to create partial shadings and maximum power point tracking to achieve the maximum power out of the installation conditions. And these are the photovoltaic current, which is regulated according to the demands. And this is the total power. You can look, the total power is always try to be the constant with respect to the panel. And with respect to the grid, we always try to have a sinusoidal voltage and current with a unity power factor. That's most important. And we are trying to keep the photovoltaic overall system in a stable condition with respect to the DC link requirement of the converters, which are integrated. So the performances are obtained with respect to the standard regulations. The most important is the total harmonic distortions and unity power factor are well regulated with the proposed ANFIS PSO algorithms. And still, we want to look at very closely how the behavior is going with the insulation and grid synchronization. So we are trying to create solar insulation from low to high, high to low. All these cases, you can have a look still from the low regulation to the high insulation condition. The grid voltage is undisturbed, and the current are creating a regulation very smooth and unity power factor. Of course, we try to do it in a reverse way from high to low insulation condition of the photovoltaic panels. Still, the unity power factor is maintained. Some distortion has been created in the current, which is a acceptable range of IEEE standards. And of course, we are looking at the grid voltages. Inverter currents, they are very smooth, and unity power factor are observed at the inverter outputs of the system which is connected to the grid. And this shows you the unity power factor operation of the grid voltage, inverter current, and grid. Always we are trying to keep the unity power factor within the limit of different insulation conditions created dynamically from the photovoltaic panels. And this is real results what we are looking at different partial condition. You can have a look. This is created the insulation condition, how the oscillation has been created by particle swarm optimization. At the same time, we have shown with ant colony algorithm optimized algorithms. The most effective is the particle swarm optimization. You can have a look different from ant colony. There is a huge oscillations observed during the partial shading operation with respect to the power, voltage, and current in case of two different control algorithms. Here we try to use the ABC and ANFIS piezo algorithms. Again, the ABC provides very smooth performances when compared to other piezo and ESO algorithms. You can have a complete look here. It's the during the insulation condition or partial distortion, the transition period is very effective, very limited. There is no huge oscillations has been created. This is a very important zone for the power, voltage, and current. We are regulating very smoothly. And this is for the combination of ANFIS and piezo, which is much superior than all other algorithms because we reduce the transient time. Even in the transient time, the oscillations are well controlled when compared to all the other three algorithms. So the effective solution for ANFIS piezo is providing more control during a partial shading condition when compared to other algorithm approaches, which can be very easily observed from the real-time testing where we observed during two different partial shading patterns. And about the tracking during the partial shading condition, the proposed ANFIS algorithm, you can have a complete clean spectrum where the voltage, current, and power are very smooth without any huge oscillations. Whereas in a conventional perturb and observe algorithm, there are huge oscillations, even which creates different harmonics, which is uncontrollable by inverters. And about the different algorithms, what we try to look at the mean square error, the root mean square error. The PSO is producing around 0.36. ASO is producing around 0.35, ABC is providing 0.34, and ANFIS, which is much lower, 3.2, which is the best out of the algorithms what we tried in artificial intelligence application for hybrid renewable energy system. And this is very important for the global point of tracking in seconds. All the cases, the ANFIS neural network, fuzzy logic, and particle swarm optimization based algorithms always goes the maximum tracking time period of 1 when compared to other algorithm which may go up to 5 and 3 for or 4 for ABC and PSO. So the combination of ANFIS plus PSO has provided very effective, robust control when compared to other algorithms. And these are the overall performances we have seen from application of different algorithms with respect to PSO. We are getting zero point 0.9 seconds is the execution time. Artificial, I mean, Antalgoni algorithm, which is zero point 0.7 seconds, and the ABC algorithm, which is 0.65 seconds, whereas the combination of ANFIS PSO, which is zero point 0.3 seconds, which is much optimized when compared to other algorithm for the execution, of course, for the root mean square error. And about the tracking efficiency, we have tried different cycles, cycle 1, cycle 2, cycle 3, and cycle 4, and we find the average value. Means what are the different cycle? Means different power scales. This is an example we tried with all the three algorithms, PSOs, ABC, and ANFIS plus PSO. This is a proposed module. We try to regulate a different power level of the panels from 200 watts to the minimum 880 watts. Then we find the average of the efficiency of the tracking. Also, in this case, 98.35 is observed when we combine ANFIS and PSO. And this is the example how the spectrum of the tracking has been carried out with the maximum power point tracking with different algorithms. So obviously, ANFIS is more effective in controlling all the renewables when connected to the inverter systems. Of course, we are also adapting more IoT, Internet of Things based applications. So for this testing, we used not the conventional sensors. We used IoT sensors without cables. So we used 4 different locations on top-proof photovoltaic panels. For this purposes, we used a modified Zeta converter. We proposed new converters, and it is controlled by particle swarm optimization augmented IoT based MPPT algorithms. Here we try to generate the PWM based on these algorithms, which generates the firing angle for the Zeta converter. Then we fed to the load. This is the simplest model of a standard photovoltaic panel, and this is the equivalent circuit of a modified Zeta converter. What is the advantage? We are able to get much higher voltage than the standard Zeta converters. The modified converter has a 2 inductor, 1 capacitors, which can able to generate a high power at the load side with respect to the voltage parameter when the device is opened. In order to adapt the new particle swarm optimization based IoT sensor, what we are doing, we start the program, we are initializing the parameters, then we check for the objective function, which is using PSO algorithm. Then we try to look at for the local searching variables of the swarm particle to achieve the best performance value. Once it determines the nodes of the neighboring performance value, we estimate the optimal solution for firing of the inverters or the converters, which is Zeta converter for the maximum power point tracking. Then we check whether we achieve the required performances. If it is yes, we stop the execution. If it is not required achieved, we go back again to find the new objective functions. For this purposes, we used parameters on inductors which are used in the converter, which is 3.5 millihenry, 320 microhenry, and capacitor which is zero point 0.6 microfarad, 1800 microfarad, and switching frequency we kept around 20 kilowatts. And the most important, how we have done the interface of IoT sensors and all these. So we use the read sensors and API call algorithm, which is a programming interface algorithms. We integrate through the algorithms and we find the switching driving systems. It's a close monitoring system. So by which we are trying to control always the parameter from the photovoltaic panel without connecting a physical voltage and current sensors. And about insulation condition is very important. We try to find insulation size of the sensor field. We use is 50 into 50 meter square. Hydration is 50. Weight of the inertia is 0.6. The coefficients we use 2 for K1 and K2 in the algorithm. The random vectors we use for the particle swarm optimization of 0 and 1. The position of the particle is the inverters and the converters for integrating with the photovoltaic panel. So this is a standard algorithm by P&O, perturb and absorb algorithm, where you can find a lot of oscillations which is generated from the photovoltaic voltage, current. Of course, the duty cycle generated by the converter is very fluctuating, and a lot of internal sub oscillations are observed with the tracking algorithms. What when we adapt the modified particle swarm optimization algorithm with IoT sensors, we have clear out all the unwanted noises which is generated in the system with a very smooth spectrum for the voltage, current, and of course the duty cycle of the converters and power are tracked to the expectation during different partial shading and even the required maximum power point trackings algorithms observed to the expectations. And this will give you overall performances of how the system is working. The system is working for a PO system. You can have a look. The completely huge oscillation is observed on a MPPT algorithm by using perturb and absorb algorithm. There are huge in sub oscillations are observed during different tracking conditions. And of course, with the power, the system which is proposed with PSO IoT is having huge oscillations created for the voltage, current, and the total power can be observed also on your right side. When we adapt the proposed PSO algorithms, the system is absolutely free of oscillation. You can have a look here. It's much reduced when compared to the classical model of MPPT algorithm. We try to provide a very smooth voltage even under huge partial shading conditions, currents, duty cycles, or behaved according to the required MPPT algorithm requirement of a PSO test algorithm. So this gives you a more clear spectrum how the smooth propagation of the voltage, current, and power are created from the proposed algorithms, a much more clear spectrum when compared to the classical model. The classical model has a huge oscillation even under the steady state condition power generation from the photovoltaic panels. And about the behaviors, I like to say that overall photovoltaic power tracking efficiency, the PSO IoT is around 99.9%, which is expected for the tracking, and ABC is 97%, and PSO which is 95%. So the proposed PSO IoT augmented algorithm is much effective, and this can be compared with three different algorithms. The computational behavior for PSO is low, simulation period is low, accuracy is very high, and the energy losses is also very low when compared to other algorithms. Tracking velocity is very high. Hardware complexity is moderate because we use IoT sensors. There are some losses of data, but we compensate by using internal loops. Cost parameters are moderate. So how we calculated the efficiency? We calculated the efficiency based on a PV power extracted by MPPT algorithms divided by the available maximum energy PV power into 100. So this is the way we calculate the efficiency, and we find the efficiency for a PSO IoT is 99.9 percentage, which is roughly comparing to other algorithms. I like to conclude for the many years we are working on hybrid renewable energy systems. We developed many algorithms based on ABC for wind and photovoltaic system. Particularly, this modified ABC algorithm is applicable for induction motor centrifugal pump application we developed. I show some very vital application for agricultural field. We also developed a PSO based evolutionary algorithm, particularly to tune the PI regulators. So to tune the PI regulators, we have developed very effectively the PSO based algorithm, which can be optimized and automated within the control loop, which changes the KP and K value according to the perturbation of the system varies. Again, we also integrated various renewable energy systems, hybrid renewable energy systems with a common DC link of inverter with wind and photovoltaics having various perturbation conditions and varying wind speed. Still, we try to control by effectively by using ANFIS based PSO algorithm for precise and accurate PV tracking for rapid convergency rates. We also adapted a modern particle swarm optimization based IoT sensor MPT algorithm, which achieves a very high efficiency when compared to other algorithms. And these are applicable for maximum power point tracking when two different renewables or four different renewables which are framing a hybrid renewable energy systems. We can use IoT based PSE PSO based algorithms. We also worked here, I have not presented, we also worked on hybrid gravitational search algorithm, which much more advanced MPPT algorithm we worked out. Particularly, the application is focused on tracking and rapid convergency of PV based permanent magnet synchronous generator for water pumping applications. So, if it is going to be a centrifugal pump induction drive, then we use ABC. When we are using a permanent magnet synchronous generators, then we use a gravitational search algorithm. So these two algorithms we develop specifically for different drives in real time. Finally, in the future, we will have many challenges, particularly on fuel cell based mainstream, because fuel cell is very expensive. In the future, all the electric vehicles are going to be fuel cells, and we need to find a low cost fuel cell prerequisite with electrolyzers, providing more efficiency by integrating with power electronics converters. When we connect multiple renewable energy systems to the grid, then we create a high voltage meditations, we create more harmonics to the grid. Then we need to investigate on instability, harmonic, voltage sag, and we have to create a modern smart grid technologies or to be employed. And in the future, it's also very important. We have shown IoT based PSO algorithms. In the future, there will be a home to grid communication and grid to home communications by using smart metering technologies. We can able to integrate all these renewables. At the same time, we have to look for system stability penetration. So there are many gaps in the future. We are also working on the charging stations for electric vehicles and energy management algorithms based on AI, which is the future demand. But we have shown these aspects on different applications, but it's also applicable for the future microgrids for charging infrastructures. So obviously there are many gaps of algorithms. Energy efficiency algorithms is needed to be bound to increase the future research. This time I like to thank my research team members, Professor Niraj Priyadarshini, Professor Mahajan Sagar Bhaskar, Dr. Kiran Pandov Maroti. Without them, is not possible. More than a decades, they are working with me, and thanks to their insight contribution on this research activity. Thank you very much. If you have any questions, I'm happy to respond.